Practice exam, unit 2. What we got here, remember how to do E and Z? You got to cut the alkene in half, right? Cut it in half this way. And so then you have bromine versus sulfur. You don't want to do red, white, and blue with this. This is just one or the other. So bromine's higher ranked because it has a higher atomic number. Problem here, OH and OH are exactly the same. So that would be neither since you can't rank those. Now you go over here, cut it in half. Carbon to carbon, tied. Carbon is bound to an oxygen, a carbon, and an H. Carbon and a carbon and an H. This one has higher priority. Oxygen beats carbon. Start there. Here, carbon to carbon, tied. Carbon, carbon, H. Carbon, HH. Carbon to carbon. They tie. Carbon versus H. This one wins. So they're on opposite sides. So that's E. And make sure you show your work on these. Lone pairs and formal charges on the molecules below. Right? Hopefully some simple stuff. Oxygen needs 3 bonds, wants 2 bonds. If it has 3 bonds, has a plus charge in a lone pair. Nitrogen wants 3 bonds, lone pair. Bromine wants 1 bond, but if it has 2, it has a plus charge. Oxygen wants 2. So this is really basic periodic table type stuff. Make sure you review that. Definition stuff, vocab stuff, constitutional isomers, right? I tell you these are the possibles. Constitution, enantiomers, diastereomers are identical. These are your possible answers. Constitutional means same molecular formula, same numbers of carbons, hydrogens, oxygens, but they're bonded differently, so that's constitutional. These two, if you flip this 180, these are actually identical, right? They're actually meso compounds too, mesomere plane. These are diastereomers because they have one the same and one different. Enantiomers would be everything opposite, so these are diastereomers. Label the chiral centers. So right, we're looking for sp3 bound to 4 different things. Things to look for. Has to be sp3, so nothing with a pi bond. Has to be bound to 4 different things, so no CH2s or CH3s. So look for atoms that have 1 hydrogen or 0 hydrogens. So we should have here 1, 2, 3, 4, 5, 6, 7 of them. Just being able to identify those things, being able to do that is important. All right. Give the mechanism with curved arrows. So again, showing arrows. You're given the steps. This looks very similar to problems we've done before. Proton transfer, right? That turns the SH into a better leaving group now, the SH2 plus. That leaves, make sure, right, giving points for charges here, make sure you balance your charges. Overall plus charge, make sure you have that. Leaving group leaves, makes a secondary allylic carbocation. It leaves, we do resonance, now we have a secondary doubly allylic carbocation. The solvent adds. Right, the solvent adds, it has 2 H's. One of those H's falls off as H plus to regenerate the catalyst, and that gets you to your final product. Again, numbering atoms, balancing your charges. This is a SN1 reaction, right? So yeah, for part 5, for step 5, again, when you have a catalyst, it needs to be regenerated, right? That's one of the things catalysts do, besides giving an alternate pathway. So what has to happen is the atom that has the plus charge here, the electrons are going to go to that atom because this nitrogen now has a lone pair. And if it's H plus has no electrons. So both those electrons in that bond go to the nitrogen. Another SN1 type problem. Again, 4 steps. Leaving group leaves, rearrange, you would say hydrogen shift. Right? Things you can look for. This is a secondary electrophile. Tertiary, you see the thing that is substituted, I gets lost, and all of a sudden that nitrogen's here on a different carbon. That tells you there's going to be some sort of rearrangement, probably. Leaving group leaves, H shift, rearrangement, make sure the electrons come from the bond. Solvent adds, deprotonate, proton transfer, H falls off again. There you go. Similar to the last one, but not exactly the same. Another SN1 reaction. So we had a question about what if you weren't given the steps, how would you know? So one of the ways you would know that resonance or a rearrangement happens is you see the leaving group is on this carbon, but the thing that adds, the thing that you end up substituting, SN1 style, ends up on a different carbon. This is where the leaving group is at, and then the thing that ends up substituting it is on a different carbon. That is an indication that either resonance or a rearrangement has taken place. All right. Show the mechanism and product of the reaction below. You're told it's SN2. So a couple things, you need to make sure the arrow is on the 180 degrees away. If you put the arrow right here, you won't get full points. Make sure it's 180 degrees away. Arrow direction matters. SN2, one step, two arrows. I don't need to change the wedges and dashes. You could have, but because the leaving group's in the plane, the nucleophile that adds can stay in that plane, and you don't need to do anything with the wedges and dashes, but there is inversion, so you gotta make sure you do that correct. Lone pairs, draw reaction, and resonance arrows. So right, we have a secondary carbocation. We're gonna do a rearrangement. H is gonna go again, the electrons move, not right, the electrons move, don't start the arrow at the hydrogen, start at the bond. That makes a secondary lone pair resonance. So, right, this is more stable because it can do resonance, and now those arrows come down. This is the most stable because everything has a full octet. So, right, thinking about stability of carbocations, this is more stable. This is the best because everybody has a full octet. All right, solvent types, just making sure you remember what OH, NH, SH, and pH are. Just don't get confused. There's no NHs. And I said add lone pairs. Make sure you read the instructions. People forget the lone pairs if I ask it this way. And I say product or aproduct. Make sure you write those two things. Aproduct, there's an OH. Aproduct, this is a CH. That's not a product solvent. NH, pH. So hopefully those make sense. Make sure you don't forget to read instructions carefully, right? Couple multiple choice questions. Which will undergo an SN2 reaction the fastest? So this is looking at electrophiles, right? So you have secondary, primary, tertiary, and tertiary. SN2 is all about that sterics. So they want a small electrophile, less steric. So this would be the one to pick. What type of reaction is shown below? You have a secondary alkyl halide, right? So it could be anything. Look at the nucleophile. It looks like it's unreactive and small. Makes you think SN1. It's protic. I look at the two products. The products are racemic. So that should tell you it's SN1. Meso compounds. Remember, meso compounds are molecules that have asymmetric centers. Asymmetric centers are sp3 hybridized, bind to 4 different things. But they are achiral because they have a mirror plane. So this one has a mirror plane, so that's the meso one. Remember, you are a meso molecule too. You have asymmetric centers and you have a mirror plane yourself. A reaction rate doubles with 2 times the concentration of the nucleophile. What type of reaction is it? So again, these are remembering those rates, right? What's involved in the rate determining step. And an SN2 and an E2 reaction, both of those involve the nucleophile. And so if you change the amount of those, that will affect the rate. SN1, nucleophile has nothing to do with it. Resonance isn't a reaction, it's resonance. SN2 is the right answer, and then rearrangements, that's different. That has nothing to do with anything. So it's SN2. So you need to know those rates as well. Last one, type of reaction for each box. Giving you the types that are possible. PT, leaving group leaves, add, substitution, elimination, rearrangement. So I told you what's possible, so don't do anything besides those. And then give the mechanism arrows. So really you're looking for bonds broken, bonds formed, right? What's going on here? Nitrogen grabs the H, OH bond breaks. That's a proton transfer. O minus, right? That's just there to balance the charge. O minus there reacts here, breaks that pi bond. That's an addition reaction. I redrew this down here. We do an elimination or make a pi bond, kick that out. That's elimination again. Numbering your atoms is always a good idea. I gave you the things. Make sure you slow down, balance your charges, add in your lone pairs. All those things would be helpful. Yeah. Again, what's not on here is E2. So I would remember that was like the last thing we did. Remember how to do chair structures. Remember how to do Newman projections, right? And rotate those things. That will be on the test, as will some of that RNS stuff in kinetics and thermodynamics stuff we talked about in class as well. Thermodynamics, remember, the more stable product, that's a thermodynamic product, right? Kinetic product is one that's the lowest hill. You should remember what exothermic and endothermic mean. Exothermic means the products are more stable than the starting materials. And then how to do RNS and rank things.